All right, so in this clip, we're going to look at the Pythagorean theorem from the point of view of inner product spaces. So if we have two vectors which are orthogonal, then the square of the magnitude of the sum is equal to the sum of the squares of the magnitudes. And so, in other words, if we're looking at the length of this squared plus the length of this squared, we get the length of this squared. Now, Pythagoras didn't think of it in exactly these terms, of course. He probably had in mind a picture that looked a lot more like this, but I don't know, you get the picture. Okay, so the proof of this one with the machinery that we've developed is actually super straightforward. So we just do everything in terms of inner products. And so I should mention here that we're in an inner product space, and we know that we're in an inner product space because we're talking about orthogonality, and you can't do that unless you have an inner product. And so that tacitly implies that the magnitude here, the norm that we're using, is going to be the one that comes from the inner product. All right, so let's see. So that means that we can compute this guy in terms of it. So this is equal to u plus v against u plus v in the inner product. And then we can use distributivity now in the first slot, and then also in the second slot, or sorry, additivity in the first and the second slot. So when we split over the first slot, we have u plus v, and v u plus v. And then we can split each of these again in the second slot. So the first one becomes u plus v. Gosh, I can't talk right today. uv. Okay, so these are both from that first one. And then the second one gives v u plus v v. Okay, so now let's see what we have. So the u against itself is magnitude u squared. And then here we have the two middle terms. So we've got uv plus, and then vu is uv conjugate, right? And if you add a complex number, so here's a picture of the complex numbers. If you add a number and its conjugate together, then what happens is the horizontal components stack and the vertical components cancel. So you end up over here at this point right here, which is 2 times the real part of z. And so that's what we get right here. We have 2 times the real part of uv in inner product. And our last guy from this term over here is the magnitude of v squared. Okay, and so now our assumption is that u and v are orthogonal. That's where we use our hypothesis. And so then that just gives us magnitude u squared plus magnitude v squared. And that's the conclusion we were trying to get to. So we're done. Okay, and now it's also worth noticing that if the field that we're working over is the reals, then the real part of uv is equal to 0 if and only if uv is equal to 0. And so in that case, we actually have the converse holding as well. So by the converse, I mean this guy right here would actually go both ways. So this is in the case when the field is equal to R. All right. So let's see. So now we have another theorem that goes right along with this one. So this is, let me see. This was, shoot, I'm just looking up the number in the book. Wait, don't they have it? Yes, they do. Okay, I thought they did. 622. So this is the parallelogram identity. And I should state it before I prove it. So it says that if we look at the magnitude of the sum of two vectors, and we add this to the difference, then we get 2 times the sum of the squares of the components. And so this is for any u and v. If we make a parallelogram out of these, then let's see. So here's our origin, and then we have u here and v here, and then this one is going to be u plus v. So then we're looking at the length of this one here, and then if we look at the difference across here, so this diagonal right here, that's actually the same thing as, it has the same length rather as u minus v. All right, so we can think of this identity as talking about the long diagonal and the short diagonal and the relation that these have to the side lengths themselves. Okay, all right, so that's the meaning of the parallelogram identity. So to prove this, wrong color, we're going to do the same sort of calculation that we had before. So in the Pythagorean theorem proof, we had u plus v quantities magnitude squared, and we saw that gave us magnitude u squared plus 2 times the real part of uv plus the magnitude of v squared. By the computation that we just did, right? So now, if we take this whole thing here and see what it would look like if we change this to a negative sign, then repeating the same calculation, we just see that we get a negative sign in front of the real part. And so now if I take these two identities and I add them together, then on the left side I have u plus v squared plus u minus v squared in magnitudes, and on the right side I have 2u magnitude squared, and then these guys cancel, and then I have 2v magnitude squared. And we're done. Nice and straightforward. Okay, so it's worth noticing. Actually, here, let's do one other thing before I make that observation. So there's another related theorem, and it's called the polarization identity. And the polarization identity says that, and there's a complex version of it and a real version of it, and the complex one is sort of complicated. So I'm just going to give you, it's not too complicated. It just has twice as many terms as the real valued one. So in the real case, the inner product of u and v is 1/4 u plus v quantity squared minus the difference u minus v magnitude squared. And so the way you prove this is probably not any big surprise. You just change this plus to a minus sign, and then you see that these guys cancel and these guys cancel, and these ones here give you a coefficient of 4. And that's it. So I just did your homework exercise for you. it's also worth noticing. Now you might be surprised and say, hey, wait a minute, you said that not every norm is associated to an inner product. But here, you just gave a formula for an inner product in terms of nothing but a norm. Well, yeah, but it turns out if your norm is not associated to an inner product, this formula for defining this widget over here, this pairing, will not actually give you an inner product. It does if and only if. So you can get an inner product from the norm like this if and only if the norm satisfies the parallelogram identity. So in some sense, the parallelogram identity is equivalent to the fact that your norm comes from an inner product. And by the way, the physical aspect of this that's neat is that these quantities here are both things that you can measure in a lab. So suppose you're looking at like superposition of like waves, like light waves or something like that, and you want to find the angle between them because you're interested in polarizing light. Well, you can actually compute that angle using the inner product in terms of things that you can measure with laboratory equipment.